What if the most familiar thing in your life, the one constant you have known since the moment of your birth, was also the universe's greatest secret? It is the invisible tether that holds you to the earth, the silent command that pulls air into your lungs, the gentle but implacable force that will one day draw the curtain on the most distant stars. This is gravity. We feel it in our bones, a deep primal connection to the very planet we stand on, an anchor in the chaotic sea of the cosmos. Its authority is absolute, its reach infinite. It gathers dust into worlds, ignites suns from collapsing clouds of gas, and choreographs the waltz of 1 trillion galaxies across the unfathomable expanse of space-time. Gravity is the grand architect of the cosmos, the master sculptor of reality, the very syntax of the physical world. Without its steady hand, the universe would be a thin, featureless soup of dissociated particles, a story with no structure, a symphony with no rhythm. And yet, for all its power, for all its undeniable presence in every moment of our existence, gravity is a ghost. It is the most profound enigma in all of science, a puzzle that has humbled the greatest minds in history from Newton to Einstein and beyond. We have charted its effects with breathtaking precision, predicting the graceful arcs of planets and the violent death spirals of black holes. But when we ask the most fundamental question of all, what times is it, the universe answers with a deafening silence. This silence is the heart of our story, the beginning of a quest that pushes humanity to the very brink of what we know and what we can ever hope to know. It is the hunt for the missing piece of creation itself. To understand the depth of this mystery, we must first journey back to a revolution that tore up the rulebook of reality. For centuries, our picture of the universe was one of elegance and continuity, a grand cosmic clockwork governed by smooth, predictable laws. But in the early 20th century, a new picture began to emerge from the microscopic realm, a picture so strange, so contrary to all human intuition, that it felt like a dispatch from another reality. This was the birth of quantum mechanics. It revealed a universe that was not smooth and continuous, but grainy, pixelated, and seething with uncertainty. At this fundamental level, reality behaves like a pointillist painting, where solid lines and gentle curves dissolve into a collection of discrete dots of indivisible packets of energy called quanta. This discovery wasn't just a minor correction, it was a complete demolition of our classical worldview. It gave us a new language to describe existence, and at the heart of this new language was a staggering revelation about the nature of force itself. Forces, the invisible pushes and pulls that govern everything, were not ethereal, mysterious fields as we had long imagined. Instead, quantum mechanics told us they were conversations. They were interactions carried out by the frantic exchange of tiny subatomic messengers, fundamental particles whose entire existence is to communicate a command. To push, to pull, to bind, to decay. Imagine two ice skaters on a frozen lake throwing a ball back and forth. Each time one catches the ball, the momentum pushes them apart. From a distance, it looks like some invisible, repulsive force is acting between them. But up close, you see the truth. The force is the ball. It's a physical exchange. The universe, at its most basic level, operates on this very principle. Every force we experience is just the universe playing an infinite game of catch with particles acting as the balls. Armed with this radical new understanding, we set out to map this hidden quantum world, to identify the messenger particles for all the known forces of nature. And the success we found was nothing short of miraculous. It led to the creation of the standard model of particle physics, arguably the most successful scientific theory in human history. It is a stunningly accurate catalogue of the universe's fundamental building blocks and the forces that govern them, a veritable periodic table for reality itself. First, we cornered the messenger for the most familiar force after gravity, electromagnetism. This is the force that generates light and lightning, that holds atoms together into molecules, that powers our technology and allows you to see the world around you. Its messenger is a particle you know well, even if you don't realize it. It is the photon, the quantum packet of light. Every ray of sunshine warming your face is a stream of countless photons, each one a tiny carrier of the electromagnetic force, a tireless messenger traveling across the void at the ultimate cosmic speed limit. But the photon does more than just illuminate. It is the universal communicator for anything with an electric charge. whispering commands that bind electrons to atomic nuclei and orchestrate the intricate dance of chemistry that makes life possible. Finding and understanding the photon was a monumental triumph, the first confirmation that forces were indeed particle exchanges. It was the first solved chapter in the quantum rulebook. Yet our universe is governed by more than just light and charge. Peering deeper into the incomprehensible furnace at the heart of the atom, we discovered two more forces, bizarre and utterly alien to our everyday experience, yet absolutely essential to our existence. Within the impossibly dense confines of the atomic nucleus, positively charged protons are crammed together, repelling each other with an electrostatic fury that should, by all rights, tear every atom in the universe apart in an instant. The fact that they do not, the fact that matter itself is stable, is owed to a force of unimaginable power, a force that acts over only the tiniest of distances, but is in that domain the most potent in all of nature. We call it the strong nuclear force. Its messenger particle is aptly named the gluon, for it is the unbreakable cosmic glue. Gluons shuttle back and forth between the quarks that make up protons and neutrons, binding them together with a strength that makes electromagnetism seem feeble by comparison. They are the jailers of the subatomic world, creating a prison from which a single quark can never escape. The discovery of the gluon was another spectacular victory for the Standard Model, explaining the very stability of the matter that constitutes our world, our bodies, and our stars. With it, we had catalogued the force that holds things together on the grandest and smallest of scales. But there was still another force, one responsible not for stability but for change. This third force is perhaps the most enigmatic of the trio, the weak nuclear force. It is a subtle and reclusive player, but its role is no less profound. While the strong force binds, the weak force transforms. It is the agent of cosmic alchemy. The weak force is what allows a neutron to change its identity and become a proton, a process known as beta decay. This might sound like an obscure subatomic quirk, but it is the very engine of the stars. It is this transformation that fuels our sun, allowing it to fuse hydrogen into helium and release the colossal energy that bathes our planet in life-giving warmth. Without the weak force, the sun would not shine and we would not be here. It governs the slow, steady tick of radioactive clocks used to date ancient artifacts and is a key player in the cataclysmic supernova explosions that forge the heavy elements like the iron in your blood and the calcium in your bones. Its messenger particles, the W and Z bosons, are unlike the others. While photons and gluons are massless, the W and Z bosons are titans, some of the heaviest fundamental particles ever discovered. Their great mass makes them sluggish and short-lived, ensuring the weak force's influence is fleeting and confined to the tight quarters of the atomic nucleus. Finding these heavy bosons in the particle accelerators of the 1980 seconds was a crowning achievement the moment the Standard Model truly came of age. The family of forces seemed complete. We had the photon for electromagnetism, the gluon for the strong force, and the W and Z bosons for the weak force. 3 forces, 3 sets of messenger particles, all accounted for, all fitting perfectly within the mathematical elegance of one extraordinary theory. It was a symphony of cosmic order, almost perfect. Almost, because as physicists celebrated their triumph, a shadow lingered in the corner of the room, a vast universe-spanning, all-encompassing shadow. Where in this beautiful quantum tapestry was gravity? The Standard Model, for all its power, said nothing about the most obvious and oldest known force of all. It described a universe of particles and forces with stunning accuracy, but it was a universe without a foundation, a building with no ground floor. The logic that had worked so perfectly for the other 3 forces seemed to demand a similar solution for gravity. If electromagnetism is an exchange of photons, and the strong force an exchange of gluons, then gravity too must be an exchange of particles. There must be a quantum of the gravitational field, a fundamental messenger that carries the command to attract. This theoretical particle, this ghost in the machine, was given a name, the graviton. On paper, its properties were easy to predict. Like the photon, it should be massless, because gravity, like light, has an infinite range. It must travel at the speed of light, because Einstein's theory of relativity tells us that gravitational disturbances, ripples in spacetime, called gravitational waves, propagate at that exact speed. And it must be its own antiparticle, a subtle detail reflecting the fact that gravity only attracts it, never repels. The theory was sound, the logic impeccable. The graviton times had times to exist. Finding it would be the final, ultimate validation of our quantum view of the universe. It would be the capstone on the magnificent edifice of the Standard Model, uniting all of creation under a single, coherent quantum language. The hunt was on, but the decades passed. We built bigger and more powerful machines, colossal rings of magnets and detectors designed to sift through the debris of subatomic collisions, searching for any sign of this elusive particle. We smashed protons together at nearly the speed of light, recreating the energies of the early universe. We built detectors of astonishing sensitivity capable of measuring distortions in spacetime, smaller than the width of an atomic nucleus. We found the Higgs boson, the particle that gives mass to all others, a discovery that filled the last major gap in the Standard Model. We directly detected the gravitational waves predicted by Einstein, a monumental achievement that opened a new window onto the cosmos. We saw the universe in a whole new way, hearing the faint echoes of colliding black holes and neutron stars from billions of light years away. We found everything we looked for, everything except the graviton. It has never, not once, appeared in any experiment. It leaves no track in our detectors, no signature in our data. It is utterly, maddeningly absent. The most ubiquitous force in the universe appears to have no quantum particle at all. This is not just a missing piece of the puzzle. It is a clue that the puzzle itself might be fundamentally wrong. The silence of the graviton suggests a deep and terrifying rift in our understanding of reality, a chasm separating our two greatest scientific achievements. On one side of this chasm is Albert Einstein's general theory of relativity. It is the theory of the very large. It describes gravity not as a force in the traditional sense, but as the curvature of a unified fabric of space and time. In this majestic vision, planets orbit the Sun, not because they are being pulled by an invisible rope, but because they are following the straightest possible path through a space-time that has been warped and dimpled by the Sun. Immense mass. It's a vision of a smooth, geometric and continuous universe, a flowing cosmic river. It works with near-perfect accuracy on the scale of planets, stars and galaxies. On the other side of the chasm is quantum mechanics, the theory of the very small. It describes a world that is not smooth but quantized, pixelated and probabilistic. It is a world of discrete particles and fuzzy uncertainties, where reality itself seems to shimmer in and out of existence. It too works with flawless accuracy on the scale of atoms and particles. Both theories are masterpieces. Both are demonstrably correct in their own domains, but they cannot both be right in their current form. They speak fundamentally different languages. General relativity is written in the language of geometry and certainty. Quantum mechanics is written in the language of probability and discreteness. When you try to combine them, when you try to describe the gravity of a single particle, for instance, or the conditions inside a black hole, or at the moment of the Big Bang, where the immensely massive meets the infinitesimally small, the mathematics breaks down completely. The equations spit out nonsensical answers, infinities that tell us we have crossed a boundary into the unknown. The smooth, flowing river of Einstein's spacetime cannot coexist with the frantic, quantized world of particles. This is the chasm where the graviton is lost. It is a particle demanded by one theory living in a world described by another, and the two refuse to speak to one another. This is why the search for the graviton is so much more than a hunt for another particle. It is a quest for a new map of reality, for a unified theory, a so-called theory of everything that can bridge this impossible gap and write the laws of the cosmos in a single, consistent language. Finding the graviton, or understanding why it cannot be found, is the single greatest challenge in physics today. It forces us to confront the possibility that our most cherished ideas about space, time, and matter may be mere shadows of a deeper, stranger reality. Does the graviton hide in extra dimensions of space curled up so small we can never perceive them? Is reality not made of particles at all, but of tiny vibrating strings of energy, with the graviton being just one of their many notes? Or is gravity fundamentally different from the other forces? Not a conversation between particles, but something else entirely. A feature of the cosmic operating system that cannot be broken down any further. To answer these questions, we must embark on an epic scientific journey. We will travel to the largest machines ever built, designed to probe the structure of reality at the highest energies. We will venture into the purely theoretical realm of the imagination, where brilliant minds are dreaming up new descriptions of the universe that defy common sense. We will meet the scientists who have dedicated their lives to this hunt, pushing the boundaries of knowledge in a search for the ultimate prize. This is not just a story about physics. It is a story about our drive to understand our place in the cosmos, to read the source code of creation, and to finally comprehend the nature of the invisible architect that shapes our world. The hunt for the graviton is on, and its outcome will redefine everything we thought we knew about the universe and ourselves. Have you ever truly considered the act of falling? Not the fear, not the impact, but the silent, inexorable pull itself. It is the universe's oldest and most intimate secret, a constant pressure you have felt every moment of your existence, a fundamental connection between your own body and the colossal sphere of rock and metal spinning beneath your feet. This relentless downward summons is so ubiquitous, so profoundly ordinary, that for most of human history, we never thought to grant it a name, let alone demand of it a reason. It was simply the way of things, the natural order. Things fall. For 2,000 years that was enough. The heavens, governed by their own perfect unknowable celestial mechanics, moved in eternal circles, while Earth, the realm of the flawed and the finite, was subject to the simple brute reality of things returning to their proper place. There were two sets of rules for the cosmos, one for the celestial ballet above, and one for the mundane stage below. They were separate, unequal, and sealed off from one another by a chasm of divine mystery. And then, in the 17th century, a mind arose that refused to accept this division. Isaac Newton, a solitary and obsessive genius, looked out upon a world ravaged by plague and saw not chaos but an underlying order, a secret text written in the language of mathematics. The apocryphal story of the apple is famous not because it is literally true, but because it encapsulates one of the most profound leaps of imagination in human history. In that simple falling fruit, Newton saw not just an object returning to the earth. He saw the moon held in its eternal silent orbit. He saw the planets gracefully pirouetting around the sun. He realized in a flash of world-shattering insight that the same invisible influence pulling the apple to the ground was the very same one reaching out across 250,000 miles of empty space to keep the moon from flying off into the void. There were not two sets of rules. There was only one. With this, Newton gave us the law of universal gravitation. For the first time, we had a single, elegant equation that could predict the fall of a raindrop and the path of a comet with equal precision. Gravity was unveiled as a force, an invisible tether connecting every object in the universe to every other object, its strength dictated by their mass and the distance between them. It was a cosmic puppet master pulling the strings of a grand, intricate clockwork cosmos. Humanity had, it seemed, deciphered God's blueprint. We could calculate the tides, predict eclipses, and even discover new planets like Neptune just by observing the subtle gravitational nudges on its neighbours. Newton's gravity was a triumph of the human intellect, a mathematical ghost that haunted the cosmos, imposing its perfect, predictable will upon all things. Yet a deep and troubling question lingered, one that gnawed at Newton himself. Asterisk. How times? How did the sun, across 93 million miles of cold, dark vacuum, tell the Earth to keep turning? How did this force communicate its intent instantaneously, without any medium to travel through? Newton had written the rules of the game, but he had no idea how the players sent their messages. He famously wrote, "I feign no hypotheses," admitting he did not know the underlying cause of this pervasive universe-defining force. For over 2 centuries we lived with this ghost in the machine. We used Newton's equations to build our world and map the heavens, all while accepting that the universe's most powerful architect operated through a kind of spooky action at a distance. Gravity was a command issued by matter and obeyed without question and without delay. The clockwork universe was perfect, but its perfection was a mystery. Then, at the dawn of the 20th century, another restless mind began to pick at the threads of Newton's magnificent tapestry. A young patent clerk in Bern, Switzerland, Albert Einstein, was not trying to overthrow our understanding of gravity. He was consumed by a different puzzle, the nature of light. His theory of special relativity, born from this obsession, had established a new cosmic speed limit. Nothing, absolutely nothing, could travel faster than light in a vacuum. This simple, immutable law was a dagger pointed at the heart of Newton's universe. If the sun were to suddenly vanish, Newton's equations implied that the Earth would instantly fly off its leash, careening into the darkness. But how could Earth know the sun was gone in that same instant? The information, the gravitational signal, would have to travel faster than light, violating Einstein's own ironclad rule. This paradox was intolerable. Either Newton's gravity was wrong or the cosmic speed limit was. Einstein, betting on light, embarked on a decade-long mental odyssey, an intellectual wrestling match with the very nature of reality. He called it his happiest thought. "Imagine," he said, a man in an elevator in a tall building, and the cable suddenly snaps. As he plummets downwards in freefall, he lets go of the keys in his hand. What does he see? From his perspective, inside the falling box, the keys do not fall. They simply float, motionless beside him. For that man, in that moment, the force of gravity has vanished. Now, imagine that same elevator, but this time it is in the blackness of deep space, far from any planet or star. A rocket attached to the top fires, accelerating the elevator upwards. The man inside feels a familiar pressure on his feet. If he releases his keys now, they will appear to fall to the floor at his feet. He has no way of knowing whether he is sitting still on the surface of the Earth, being pulled by gravity, or accelerating through empty space. This was the revelation. Gravity, Einstein realized, was indistinguishable from acceleration. They were two sides of the same coin, and if this was true, then gravity was not a force at all. It was something far more profound, something woven into the very architecture of existence. This was the birth of general relativity. Einstein proposed that the three dimensions of space and the single dimension of time are not a static, passive backdrop for the events of the universe. Instead, they are fused together into a single dynamic, four-dimensional continuum spacetime. And this spacetime is not flat. It is a fabric, a substance that can be bent, warped, and curved by the presence of mass and energy. Think of it like a vast, stretched rubber sheet. Place a heavy bowling ball, our sun, in the center. The sheet dips, it curves. Now roll a small marble, the Earth nearby. The marble doesn't fly in a straight line. It follows the curve in the sheet created by the bowling ball, spiraling around it in what we perceive as an orbit. There is no invisible tether pulling the marble towards the ball. The marble is simply following the straightest possible path through a curved landscape. It is following the geometry of the universe. This is gravity. Not a force that propagates times through time-space, but a feature times of time-space-time itself. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun is telling space-time how to curve, and space-time is telling the Earth how to move. It was an idea of breathtaking elegance and audacity. It explained Newton's lingering mystery of action at a distance. There was no instantaneous message. If our sun vanished, it would create a ripple in the fabric of space-time, a gravitational wave that would travel outwards at the speed of light. Only when that ripple reached Earth a full 8 minutes later would our planet's orbit finally change. Newton's ghost was banished, replaced by the tangible physical curvature of the cosmos. The theory made stunning predictions. It suggested that the immense gravity of the Sun should not only bend the path of planets, but it should also bend the path of light itself. During a total solar eclipse in 1919, expeditions led by Sir Arthur Eddington photographed the stars near the Sun's darkened limb. They found their positions had shifted, their light deflected by the Sun's gravitational well, precisely as Einstein's equations had foretold. Overnight, Einstein became a global icon. The clockwork universe was gone, replaced by a dynamic, elastic, geometric cosmos. a universe more bizarre and more beautiful than we had ever imagined. Gravity was the silent architect of our destinies, shaping the paths of planets, stars, and even entire galaxies as they sailed upon the currents of a four-dimensional ocean. For decades, general relativity has reigned supreme as our description of the macrocosm. It predicts the existence of black holes, cosmic sinkholes in space-time so dense that not even light can escape their grasp. It explains the subtle wobble in the orbit of Mercury that had baffled Newtonian astronomers. It accounts for gravitational lensing, where the gravity of entire galaxy clusters acts like a cosmic telescope, bending and magnifying the light of objects far behind them. And it tells us that time itself is not absolute, but a river that flows at different speeds depending on where you are in a gravitational field, a phenomenon known as time dilation. Every test we have thrown at general relativity, it has passed with flying colours. It is by all measures one of the most successful and elegant theories in the history of science. It is the poetry of the large, the majestic, the cosmic. But here at the peak of its triumph, our story takes a dramatic turn. Because while Einstein was reimagining the universe on the grandest of scales, a second parallel revolution was taking place in physics. A journey not into the vastness of space, but into the impossibly small, into the very heart of the atom. This was the birth of quantum mechanics. And if general relativity is a sweeping, elegant symphony, quantum mechanics is a chaotic, frenetic blast of punk rock. It describes a world that defies all common sense. A world of probabilities, not certainties. A world where particles can be in multiple places at once, where reality itself seems to flicker in and out of existence in a seething, energetic foam. In this quantum realm, the smooth, predictable geometry of Einstein's universe dissolves. Here, everything is quantized, chopped up into discrete, indivisible packets of energy. This new theory proved just as powerful in its own domain as Einstein's was in his. Quantum mechanics gave us the laser, the transistor, the computer chip, and the foundation of modern chemistry and biology. It successfully explained 3 of the 4 fundamental forces of nature. Electromagnetism, the force that holds atoms together, is carried by a quantum particle, the photon. You are seeing these words right now because photons are carrying that information from the screen to your eye. The strong nuclear force which binds protons and neutrons together in the atomic nucleus is mediated by particles called gluons. The weak nuclear force responsible for radioactive decay is transmitted by W and Z bosons. Each force a field. Each field with its own messenger particle, its own quantum. This framework, known as the Standard Model of Particle Physics, is our definitive instruction manual for the subatomic world. It is a testament to what we can understand when we probe the building blocks of reality. And now we arrive at the precipice of the great gaping chasm in modern physics. We have 2 towering achievements of human intellect. General relativity, the flawless theory of the very big of planets, stars, and galaxies, describing a smooth, deterministic, geometric universe. And quantum mechanics, the equally flawless theory of the very small of atoms and particles, describing a fuzzy, probabilistic, quantized world. Both theories have been tested to unimaginable precision. Both are in their own realms correct, and yet they are utterly, fundamentally, and violently incompatible. They cannot both be right in their current forms. They speak different languages. They give different answers to the same questions. Try to use general relativity to describe the singularity at the heart of a black hole, a point of infinite density, and the equations break down, producing nonsensical infinities. Try to use quantum mechanics to describe the curvature of space-time on the smallest possible scales, and you get a chaotic, nonsensical mess of probabilities. The universe we live in is one universe. The laws that govern the dance of a galaxy must, at some fundamental level, be the same laws that govern the flicker of a subatomic particle. But our 2 greatest theories stand on opposite sides of a conceptual divide, refusing to acknowledge one another like 2 rival gods ruling separate, incompatible creations. This is the central crisis of modern physics. It is the Holy Grail. The reconciliation of these 2 pillars, the creation of a single, unified theory of quantum gravity, a theory of everything, is the most profound challenge we have ever faced. How do we bridge this impossible gap? How do we unite the geometric elegance of Einstein with the probabilistic chaos of the quantum? The search for an answer begins with a simple logical question. If the other three fundamental forces are all quantum phenomena mediated by messenger particles, then why should gravity be any different? If space-time can be bent and warped as Einstein so brilliantly proved, then according to the rules of quantum mechanics, those bends and warps, those gravitational waves should themselves be quantized. They must be made of something. There must be a fundamental particle of gravity, a tiny discrete packet of gravitational information. An elusive ethereal messenger that communicates the curvature of the cosmos from one place to another. We have a name for this ghost. It is the Graviton. It is the missing piece of the puzzle. The hypothetical key that could finally unlock a unified understanding of our universe. It is the particle that must exist if our entire conception of physics is to make sense. And yet we have never seen one. We have never detected its presence. It remains a theoretical necessity, a whisper in our equations. The quest to find it, to prove its existence, is not just a scientific curiosity. It is a hunt for the very soul of reality, a journey to understand why the universe is the way it is, and to finally read the single unified law that governs all of creation. But this hunt will take us to the very edge of what is possible, demanding that we build experiments of unimaginable scale and sensitivity to search for a phantom that may not want to be found undefined. And so physics arrived at its great schism. On one side, the majestic sweeping tapestry of Einstein's space-time, a continuous flowing fabric warped by mass and energy. On the other, the frenetic shimmering world of the quantum, a realm of discrete packets, probabilities, and ghostly particles that communicate through messengers. For decades, these two pillars of our understanding stood in stark, silent opposition, describing the same universe in languages that were mutually incomprehensible. Yet, in the world of the very small, a revolution was already underway, a string of triumphs so profound it seemed no puzzle in nature could resist its logic. This was the rise of the standard model of particle physics, a theory so successful, so breathtakingly accurate, it became humanity's codified recipe for reality itself. It began not with gravity but with light. For centuries we saw light as a wave, but the quantum revolution revealed its other face, the photon, a single, indivisible packet of electromagnetic energy. Physicists realized that the familiar push and pull of magnets, the crackle of static electricity, all of it could be described as an endless exchange of these phantom-like messenger particles. When two electrons repel each other, what you are truly witnessing is them playing a frantic game of catch, tossing photons back and forth. Quantum field theory provided the mathematics for this game, a glorious framework that took a force and reimagined it as a conversation carried by a particle. With electromagnetism conquered, the architects of the quantum world turned their gaze toward the strange forces hidden deep within the atomic nucleus. There they found the weak nuclear force, the engine of radioactive decay, responsible for the slow transformation of elements inside stars. It too, they predicted, must have its messengers. Their search led them to the massive W and Z bosons particles, so heavy they could only carry their message over infinitesimal distances before vanishing. Finding them required building colossal machines to shatter matter with unimaginable energies, but find them we did. Then came the strong nuclear force, the cosmic superglue that binds quarks together inside protons and neutrons, a force so powerful that it never ever lets go. Its messenger was dubbed the gluon, a particle that carries a color charge and in a bizarre twist of quantum logic interacts with itself, creating a bond that grows stronger the more you try to pull it apart. The photon, the bosons, the gluon, one by one, three of the four fundamental forces of nature had been successfully quantized, translated into the language of particles. A grand symphony of existence was being written, with each force playing its part, each with its own carrier, its own rules of engagement. By the late 20th century, the Standard Model stood as a monumental testament to human intellect, a theory that could predict the outcome of particle collisions with astonishing precision. It was a moment of supreme, perhaps even dangerous confidence. The recipe seemed perfect. The method was proven. And there, standing apart, aloof and mysterious, was the fourth and final force, gravity. The oldest, most familiar force in our lives, yet the only one that refused to join the quantum dance. The temptation was irresistible. If the method worked for the other three, why not for the fourth? The logical next step, the final summit to be conquered, was to take Einstein's hallowed equations for spacetime and subject them to the same quantum treatment. The process began on chalkboards and in the quiet minds of theoretical physicists. They took the smooth geometric curves of general relativity and tried to break them down into discrete quantum units. They imagined the fabric of spacetime not as silk, but as a fine-grained, pixelated net. And as they worked through the fiendishly complex mathematics, something extraordinary began to emerge from the equations. A prediction. If gravity, like the other forces, was to be a conversation between particles, it too must have a messenger, a quantum of the gravitational field, a particle that would carry the command bend to the fabric of spacetime itself. They gave it a name that was at once simple and profound, the graviton. From the architecture of the theory, its essential properties could be deduced long before one could ever be seen. We know gravity's influence stretches across the entire universe. Its reach is infinite. For a force to have infinite range, its messenger particle must have zero mass. Just like the photon, the graviton would be a massless traveler forever journeying at the speed of light. But it would be fundamentally different from the photon in one crucial way, a way that dictates the very character of gravity. This difference lies in a quantum property called spin. You can think of a particle's spin not as a literal rotation, but as its intrinsic angular momentum, a measure of how it looks from different directions. A photon has a spin of 1. This spin, one nature, is what allows electromagnetism to be both attractive and repulsive. A positive charge and a negative charge pull together, while like charges push apart. The graviton, the mathematics insisted, had to be different. Its spin had to be 2. This wasn't an arbitrary choice. It fell directly out of the nature of Einstein's theory. While a spin, one force carrier like a photon, is described by a vector, a spin, 2 particle, is described by a more complex mathematical object called a tensor. What this means in a tangible sense is profound. A spin 2 particle interacts with the mass energy of an object, not its charge. And because mass energy is always positive, there is no such thing as negative mass. The force it mediates is always the same. It is always attractive. The graviton's spin 2 nature is the deep quantum reason why gravity always pulls, never pushes. It's a kind of double-handed grip on the fabric of reality, a celestial gyroscope that doesn't just point in one direction but creates a tidal distortion, stretching and squeezing space-time in 2 directions at once as it passes. So the theory was beautiful, it was elegant, it unified the grand cosmic scale with the quantum world, completing the quartet of forces. The graviton was the missing piece, the final note in the symphony. There was just one problem, a problem so immense, so gargantuan in its scale that it would halt progress for a century and push physics to the very edge of reason. The theory existed on paper, a perfect mathematical ghost, but in the real world, the graviton was nowhere to be found, and the reason for its absence stems from the most baffling property of the very force it is supposed to carry. It's almost unbelievable, its laughably insignificant weakness. You have an intimate experience with this weakness every single day, though you may not realize it. Take a simple refrigerator magnet, a tiny sliver of metal. Watch as it effortlessly lifts a paperclip, defying the gravitational pull of the entire planet Earth beneath it. In that simple act, the electromagnetic force exerted by a few grams of magnetized iron overwhelmingly defeats the gravitational force of 6 trillion kilograms of rock and metal. One force, a titan, the other a ghost. This isn't just a small difference, it is the single greatest disparity in all of nature. If you were to compare the strength of the electromagnetic repulsion between 2 protons with their gravitational attraction, you would find gravity is weaker by a factor of 10 to the power of 36. That's a 1 with 36 zeros after it. It's a number so large that our minds struggle to grasp its scale. To write it out longhand would be an exercise in absurdity. It is a trillion. It is more than the number of stars in the observable universe. It is more than the number of grains of sand on every beach and in every desert on our planet. This is not a quantitative difference, it is a qualitative one. The strong, weak, and electromagnetic forces operate on a stage of immense power and drama. Gravity, by comparison, is a whisper in a hurricane. It is the faintest bass note in a cosmic orchestra that is otherwise screaming at full volume. And it is this fundamental feebleness that makes its messenger, the graviton, the most elusive particle in the universe. The strength of a force is directly related to how readily its messenger particle interacts with other particles. Physicists call this a coupling constant. The photon messenger of the vibrant electromagnetic force is a social butterfly. It couples eagerly to anything with an electric charge. It is absorbed, emitted, and scattered with incredible ease. This is why you can see photons from the sun strike the world around you, are absorbed by some atoms, re-emitted, and a tiny fraction of them eventually enter your eye, coupling with the molecules in your retina to create a signal. Billions upon billions of these interactions happen every second for every person on Earth. The gluons that bind your atoms together are even more furiously interactive, coupling so strongly they can never be seen in isolation. They are prisoners of their own strength. The graviton, however, is the ultimate hermit. Because gravity's coupling constant is so infinitesimally small, a graviton interacts with matter with a reluctance that borders on the absolute. A single graviton born in some cataclysmic cosmic event could travel through light years of solid lead and have virtually no chance of being stopped or scattered. It would pass through you, through the Earth, through the sun itself, as if you were all transparent ghosts. Its message of gravitational curvature is delivered, but the particle itself barely acknowledges the existence of the matter it is commanding. This is why we cannot see them. It's not that they aren't there. If the theory is correct, you are being bombarded by a sea of gravitons at this very moment, from the Earth, from the sun, from the distant churning of galaxies. They are flowing through you, defining the very space you occupy, but they are so fantastically unwilling to interact that they leave no trace of their passage. This incredible weakness presents an almost insurmountable barrier to our conventional methods of discovery. We found the W and Z bosons by building magnificent machines, particle accelerators, like the Large Hadron Collider circular tunnels, dozens of kilometers in circumference. Within these rings, we accelerate protons to nearly the speed of light and smash them together, creating fireballs of pure energy from which exotic, short-lived particles can precipitate, if only for a fraction of a second. The energy of the collision, dictated by Einstein's E equals mc squared, determines what particles can be born from the crucible. We can create heavy quarks, massive bosons, even the Higgs boson itself. So, could we simply build a big enough collider to create and detect a graviton? Here we crash headfirst into the brutal mathematics of the problem. Because gravity is so weak, the energy required to force its quantum nature into the open to produce a graviton in a collision that we can clearly identify is simply astronomical. An identifiable graviton wouldn't just emerge from any old collision. It would require squeezing energy into a volume so dense that gravity's effects become comparable to the other forces. The calculations deliver a chilling verdict. To have even a reasonable chance of producing a detectable graviton, we would need a particle accelerator powered by an energy that is a quadrillion times greater than the Large Hadron Collider. Think about what that means. An accelerator that powerful would not be kilometers in circumference but light years. It would encircle the entire solar system. Its energy budget would exceed the total energy output of the sun over thousands of years. We do not have the materials, the energy, or the technology to build such a machine, and we likely never will. But the problem is even deeper, more paradoxically cruel than mere engineering limitations. For even if we could somehow assemble this godlike machine, we would be confronted by the ultimate catch-22, a law of nature that slams the door in our face. If you concentrate that much energy into such a small space, the very condition required to see a graviton, the energy itself, according to general relativity, would warp space-time so severely that it would collapse under its own gravity. It would form a black hole. Our ultimate experiment to probe the quantum nature of gravity would inevitably create an object whose interior is by definition causally disconnected from the rest of the universe. Our probe would be devoured by its own subject. The act of observation would destroy the very possibility of observing. This is not a technological hurdle. It is a fundamental limit imposed by the universe itself. It is a signpost, a warning that we are approaching a new territory, a realm where our trusted laws of physics begin to fray and break down completely. We have given this frontier a name, the Planck scale. The Planck scale is not a place, but a threshold. It is a set of fundamental units derived by the physicist Max Planck from the universal constants of nature, the speed of light, the gravitational constant, and Planck's constant itself. It defines the Planck length about 1/100th of a billionth of a trillionth of the width of a proton, the shortest possible meaningful distance. It defines the Planck time, the time it takes light to cross that distance, the shortest possible tick of a cosmic clock. And it defines the Planck energy, the colossal energy needed to probe physics at that scale. This is the domain where the universe's source code is written. It is the energy level where gravity, that feeble whisper, finally sheds its weakness and screams with a force equal to that of the strong, weak, and electromagnetic forces. It is the point of true unification. At the Planck scale, our comfortable picture of a smooth, gently curving spacetime utterly collapses. Spacetime itself is predicted to dissolve into a maelstrom of quantum uncertainty, a chaotic, boiling quantum foam of virtual black holes and wormholes popping in and out of existence in an instant. Here, cause and effect may lose their meaning. The very concepts of before and after, of here and there, may become undefined. This is the wall at the end of physics as we know it. And it is on the far side of this wall, in this incomprehensible furnace of creation, that the graviton truly lives and has its being. Our particle accelerators can only gently tap on this wall, hoping to hear a faint echo from the other side. They cannot break it down. We are left in a state of profound cosmic frustration. We have a beautiful logical prediction for the particle of gravity, a particle whose properties flow naturally from the union of our two greatest theories. The graviton should exist. It provides the missing link, the final piece of the puzzle, yet it is guarded by an energy barrier so immense, so absolute, that direct detection seems not just difficult, but a fundamental impossibility. The universe seems to have conspired to show us the tantalizing blueprint for a quantized theory of gravity, while simultaneously making it impossible for us to ever build it, to ever test it, to ever hold its final crucial component in our resummation. Hands. The hunt for the graviton has led us to the edge of an abyss, the Planck scale, and we find ourselves staring into a darkness our current physics cannot penetrate. If a direct collision is impossible, if the heart of the storm is forever shielded from our view, must we give up the hunt? Is the graviton doomed to remain a mathematical phantom, a ghost in the machine of our theories, or are there other ways to listen? To search for the faintest, most ancient whispers of quantum gravity, not in the manufactured fury of a collider, but in the echoes of cosmic events so violent they could shake the very fabric of space-time itself. Perhaps the clues are not in what we can create, but in what the universe has already created for us. And so, after decades of searching, the silence became the answer. The hunt for the graviton, that ghost particle we believed would complete our cosmic puzzle, had led us not to a triumphant discovery, but to a wall of sheer, insurmountable scale. The grand detectors we had built instruments so sensitive they could feel the fabric of space-time ripple from collisions a billion light-years away were deaf to the quantum whisper of a single graviton. The particle we sought was not merely elusive. The cold, hard mathematics revealed it to be almost perfectly invisible, a phantom hiding in plain sight. To understand the depth of this challenge, you must first appreciate the force we are trying to dissect. Gravity, the architect of galaxies and the anchor of worlds, is paradoxically incomprehensibly weak. Every time you lift your foot from the ground, the electrochemical signals in your muscles are overpowering the collective gravitational pull of an entire 6 sextillion-ton planet. It is a force of cosmic patience, winning its battles not with brute strength, but with infinite reach and persistence. The other forces of nature are spectacularly more sociable. An electron and a positron will annihilate each other in a flash of gamma rays, their interaction a violent, unmissable event. The strong nuclear force binds protons together with such ferocity that it takes the heart of a star to break them apart. Even the neutrino, the universe's most famous recluse, a particle that can pass through a light-year of solid lead untouched, is a boisterous extrovert compared to the graviton. calculations revealed the staggering truth. To build a particle detector with a reasonable chance of spotting a single high-energy graviton emanating from a source like the Sun, you would need a shield of lead so dense, so impossibly vast, it would stretch for thousands of light-years. But the problem is even more profound. The very act of building such a detector, of concentrating so much mass and energy in one place, would cause it to gravitationally collapse. Your graviton detector would become a black hole long before it ever registered a single event. It was a cosmic catch, 2-2, a law of nature preventing us from observing its own machinery. The universe, it seemed, had constructed a lock and then thrown away the key, leaving us staring at a door we could never hope to open. This profound realization sent a shockwave through the world of physics. It was more than just a failed experiment. It was the failure of an entire methodology. For a century, our path to understanding had been paved with a partnership between theory and detection. A theorist would predict a particle, an experimentalist would build a machine to find it, and with each discovery, from the positron to the Higgs boson, our standard model of particle physics grew more complete, more powerful, more true. But gravity refused to play by these rules. The trusted path had crumbled into a dead end. We stood at a precipice, faced with a choice that would define the next era of science. Do we continue building ever larger, ever more futile machines, hoping for a miracle, or do we accept the message the universe was sending us, that you cannot find the graviton because you are looking for it in the wrong way? Focus had to shift. If we could not capture the particle directly, perhaps we could deduce its existence from a higher, more fundamental truth. The hunt for a single particle transformed into a far grander, more audacious quest, the search for a complete theory of quantum gravity. It was a pivot from the world of concrete and steel to the ethereal realm of pure mathematics, from observation to imagination. We had to abandon the comfortable shores of the known and sail into an ocean of mind-bending possibilities, hoping one of them would lead us back to the familiar reality we see around us. From this crucible of intellectual necessity, two titanic and radically different ideas began to emerge, each offering a new language to describe the cosmos. One of these ideas did not begin with gravity at all. It was born from attempts to understand the tangled mathematics of the strong nuclear force in the 1960 seconds. It was a peculiar framework, one that saw fundamental particles not as infinitesimal points but as something else entirely. It saw them as tiny, one-dimensional vibrating filaments of pure energy. This was the dawn of string theory. In this new vision of the universe, everything you see, everything you are, is a symphony. The electron is not a dot but a string vibrating in a particular pattern, producing a specific note. The quark is another string playing a different chord. The photon, the particle of light, is yet another. All the particles and forces that make up our reality are just the unique resonant frequencies of these fundamental cosmic strings, a universe of music played on an orchestra of unimaginable smallness. Initially, the theory was a mathematical curiosity beset with problems. It predicted particles that didn't exist and required a bizarre number of spatial dimensions, not the 3 we experience, but 9 or even 10. For years, it was relegated to the fringes of theoretical physics, an elegant but seemingly flawed piece of mathematics. Then, in the 1980 seconds, a stunning revelation brought it roaring back to the forefront. As physicists explored the vast spectrum of possible vibrations these strings could exhibit, they found one that was utterly unique. It was a closed loop of string vibrating in a very specific way, and the particle it described had properties that were startlingly familiar. It had zero mass. It had a quantum spin of 2, and it interacted with a strength proportional to an object's mass energy. This was no random particle. The mathematics was unequivocal. String theory hadn't just made room for gravity. It had times demanded times it. The specific vibration of that closed loop of string was in every respect the graviton. It fell out of the equations not as an awkward addition, but as a natural, essential part of the cosmic composition. For the first time, we had a quantum theory that did not just accommodate gravity, but predicted it. It was a moment of breathtaking breakthrough. The graviton was the song of a closed string, and the force of gravity itself was the collective hum of this countless vibrating chorus echoing through the cosmos. But to accept this beautiful picture, you must also accept its startling consequences. String theory's insistence on extra dimensions of space was not a bug, but a feature. Where are these other dimensions? The theory suggests they are all around us, but curled up or compactified to a scale so infinitesimally small that we can never perceive them directly. Imagine a garden hose. From a great distance it appears as a one-dimensional line. You can only move forward or backward along its length, but for an ant walking on its surface, the hose has a second dimension, the tiny curled-up circumference it can crawl around. In the same way, string theory proposes that at every single point in our familiar three-dimensional space, there exists a hidden complex 6- or 7-dimensional shape called a Calabi-Yau manifold, a universe in miniature, curled up smaller than an atom. Our particles, our entire existence, are essentially confined to a brain, a three-dimensional membrane floating within this higher dimensional reality, which physicists call the bulk. We are like ships sailing on the surface of a vast, deep ocean, aware only of the 2 dimensions of the water's surface, utterly oblivious to the profound depths beneath us. This vision offers a tantalizing explanation for gravity's perplexing weakness. In string theory, the particles and forces of the standard model electromagnetism, the nuclear forces, are the vibrations of open-ended strings whose endpoints are permanently anchored to our three-dimensional brain. Their influence is confined to our reality, concentrating their power. But gravity is different. The graviton is a closed loop of string. It has no endpoints to tie it down. It is free to roam not just within our brain, but throughout the full higher dimensional bulk. This means the gravity we feel is just a fraction of its true strength, a pale shadow of its power, because most of its influence is constantly leaking away into these hidden extra dimensions. It's as if the other forces are shouting directly into your ear, while gravity is shouting from another room, its voice muffled by the intervening walls of reality. This isn't just a convenient excuse, it's a core prediction. It recasts the weakness of gravity not as a strange accident, but as the first piece of experimental evidence for the existence of dimensions beyond our own. The search for the graviton had led us to a place that felt more like science fiction than science, a universe far stranger and more complex than we had ever dared to imagine. It presented a magnificent, unified picture, but one that came at the cost of a reality we could no longer fully grasp. But what if this entire approach, this very idea of particles moving through a pre-existing stage of space-time, was the fundamental mistake? As string theory was capturing the imagination of a generation of physicists, a rival idea began to blossom from a completely different seed. This second great contender didn't start with particles and try to fit gravity in. It started with Einstein's own masterpiece, general relativity, and took his most profound insight that gravity times the geometry of space-time to its logical quantum conclusion. If space-time can bend, warp, and ripple, its proponents asked, then why can't it be made of something fundamental? This is the central premise of loop quantum gravity. It proposes that space-time itself is not the smooth, continuous, infinitely divisible background we perceive. Instead, it is a fabric, and if you could zoom in to the smallest possible scale, the Planck scale, 100 billion times smaller than a proton, you would see that this fabric is not smooth at all. You would see that it is woven from discrete, indivisible threads. It is granular. It is quantized. Loop quantum gravity, or LQG, asks you to discard the idea of an empty stage. There is no stage. There are only the actors, the relationships between events. The theory describes the universe as an evolving network of connections, a web of abstract links called a spin network. Each node in this network represents a quantum chunk of volume, an atom of space, the smallest possible unit of three-dimensional existence. You cannot have half a quantum of volume, just as you cannot have half a water molecule. These are the fundamental pixels of reality. These atoms of space are not times in time-space. They times are time-space. And the links between them define their geometric relationship, weaving the very fabric of the cosmos. The universe in this view is a titanic work of quantum pointillism, creating a seemingly smooth picture from an uncountable number of discrete dots. And what about time in LQG? Time also loses its familiar continuous flow. What we perceive as the smooth passage of time is actually the frantic step-by-step reconfiguration of this spin network, a series of discrete computational ticks of the cosmic clock. The universe is a colossal quantum computer, and its program is the evolution of geometry, one Planck time step at a time, creating a cinematic illusion of motion we call the future. So, where is gravity in this picture? Where is the graviton? This is where LQG presents its most radical departure. In loop quantum gravity, gravity is not a force carried by a particle at all. There is no graviton traveling through space. Instead, gravity is nothing more and nothing less than the physical reality of the geometry of the quantum spin network itself. It times the curvature of the connections between the atoms of space. When a massive object like a planet sits in this network, it doesn't emit gravitons. It simply alters the pattern of the weave around it, changing the probabilistic geometry of the links pulling on the threads of space itself. Another object moving nearby doesn't feel a force. It simply follows the new distorted pathways laid out for it in this quantized, bumpy landscape. Gravitational waves, the ripples detected by LIGO, are not a stream of gravitons in this model. They are quantized shockwaves, traveling times through times the spin network like a shiver propagating across a spider's web, a collective excitation of the geometry of space itself. The graviton, the particle we had been hunting for, simply doesn't exist as a fundamental entity in this framework. The quest to find it was a category error, like trying to find the particle of wetness in a collection of water molecules. The property we were looking for was an emergent phenomenon of the underlying system, not a component within it. And here the two great paths to quantum gravity diverge dramatically, presenting us with two profoundly different, mutually exclusive visions of reality. In one, the universe is a symphony of vibrating strings in 10-dimensional spacetime, and gravity is a unique note in that cosmic music, its weakness a sign of worlds beyond our own. In the other, the universe is a dynamic computational network of quantized geometric relationships, and gravity is the structure of the network itself, with no need for a messenger particle. String theory is a theory of unification, seeking to describe all forces and particles within a single elegant framework. Loop quantum gravity is more conservative in its ambition, focusing solely on quantizing Einstein's theory of gravity on its own terms, without necessarily including all the other forces of nature. One is a theory of everything, the other a theory of quantum spacetime. Both are built upon sublime and formidable mathematics. Both are as of now almost completely untestable. They make predictions not about what we can see in our giant particle colliders, but about the nature of black hole singularities and the state of the universe moments after the Big Bang realms far beyond our current experimental reach. The hunt for the graviton had led us to this fork in the road, a theoretical schism that has defined fundamental physics for the last 30 years. The question was no longer simply where is the graviton? It had become what is space-time. Is it a stage, or is it the actor? A vessel for reality, or reality itself? The answer would determine the future of physics, and to find it, we would have to learn how to ask the universe a whole new set of questions. The silence from our detectors is deafening. It is a verdict delivered not in words but in an abyss of emptiness, a profound cosmic stillness where a storm of gravitons was meant to rage. We have built the most sensitive ears in human history, monuments of engineering designed to listen for the faintest whisper of spacetime's quantum heartbeat, and they have heard absolutely nothing. This colossal failure, this grand and expensive silence, could be misinterpreted as an ending. A final definitive statement that the graviton, the ghost we have chased for a century, simply isn't there. But for the theoretical physicist, this is not an end. It is a violent, necessary pivot. When the path of direct experimentation crumbles into an impassable chasm, humanity does what it has always done. We turn from our tools of metal and silicon to the one instrument powerful enough to bridge the infinite. We turn to the human mind. The search for the graviton now leaves the clean rooms and vacuum chambers behind, ascending into a far stranger and more treacherous domain, the landscape of pure thought of mathematics so esoteric it borders on philosophy. Here in this abstract wilderness, the hunt continues, but the quarry has changed. We are no longer searching for a mere particle. We are searching for a new description of reality itself, a new universe, and within it, the reason for gravity's maddening invisibility. Two monumental theories now stand as our guides into this unknown territory, each a cathedral of logic built over decades of relentless intellectual labor. They begin from the same premise that the smooth, placid fabric of Einstein's spacetime must, at its deepest level, be a roiling quantum sea. Yet they arrive at visions of the cosmos so wildly divergent, so utterly incompatible, they represent a fundamental schism in our understanding of everything. On one side, there is a theory of sublime elegance, a proposal that the entire universe, with all its particles and forces, is not made of points but of music. This is string theory. It asks you to forget everything you know about fundamental particles as dimensionless dots. Instead, it invites you to imagine an infinitely small, one-dimensional filament of energy, a string, vibrating in the quantum foam. Just as a single violin string can produce a rich spectrum of notes by vibrating at different frequencies, this single fundamental entity can manifest as every particle we have ever discovered. One vibrational mode, one specific note in this cosmic symphony produces an electron, another a quark, another a photon. The universe in this view is a vast interconnected orchestra, and its fundamental laws are the rules of its harmony. And within this grand composition there is one very special note. It corresponds to a string that is not an open filament with ends but a closed continuous loop. This loop has precisely the properties we would expect of the graviton. It is massless, it travels at the speed of light, and it possesses the exact amount of quantum spin required to transmit the force of gravity. String theory doesn't just accommodate the graviton, it demands its existence. The particle of gravity emerges from its mathematics not as an afterthought, but as a necessary and unavoidable consequence of the universe being made of strings. For a moment, this feels like a profound breakthrough, a moment of exquisite clarity. The theory's internal consistency is breathtaking. But as we celebrate this apparent victory, string theory whispers a startling and uncomfortable truth. The mathematics that so beautifully describes this symphony of strings, the equations that give rise to the graviton, simply do not work in the universe we know. They are internally inconsistent, plagued by mathematical anomalies that render them nonsensical unless we are willing to make a truly radical concession. The equations only achieve their perfect harmony if the strings are allowed to vibrate in a universe with not 3 spatial dimensions but 9. Not 4 dimensions of space-time but 10. This is the staggering price of admission to the world of strings, a reality with 6 extra spatial dimensions curled up and hidden from our senses, existing at every single point in our familiar space, yet so microscopically small that we have never perceived them. It's a concept that shatters our most intuitive picture of the world. Where could these dimensions possibly be? Imagine a long, thin garden hose stretched across a vast lawn. From a great distance, it appears as a simple one-dimensional line. You can only move forward or backward along its length. But for a tiny ant crawling on its surface, the reality is far richer. The ant can move forward and backward along the hose, but it can also walk around its circular circumference. What we perceived as one dimension was in fact 2. String theory proposes that our entire 3-dimensional universe is like the surface of that hose. We are the ants living out our lives on a membrane, a brain, as physicists call it, completely oblivious to the tiny curled-up dimensions that exist at every point beneath our feet. This spectacular, almost unbelievable revelation does more than just make the theory work. It offers for the first time a potential solution to the very mystery that began our entire quest, the baffling weakness of gravity. In the grand hierarchy of forces, gravity is the runt of the litter trillions upon trillions of times weaker than electromagnetism or the nuclear forces. Why can a simple refrigerator magnet, with its minuscule electromagnetic field, defy the gravitational pull of the entire planet Earth? String theory provides a breathtakingly elegant answer. The particles of matter and the carriers of the other forces, the electrons, quarks, and photons, are all manifestations of open strings. Their ends, like roots, are permanently anchored to our 3-dimensional brain. They are stuck here, living and interacting entirely within our universe. But the graviton, the closed loop of string, is different. It has no ends to anchor it. It is a free agent untethered to our reality. And so string theory suggests the graviton is the only particle in the standard model that is free to explore the full 10-dimensional space, the higher dimensional reality that physicists call the bulk. What this means is that the gravity we feel, the force holding us to our chairs, the force keeping Earth in orbit around the Sun, is merely a tiny fraction of its true intrinsic strength. Most of gravity's influence isn't here at all. It is constantly, ceaselessly leaking away from our brain, spreading its power thinly across all those extra hidden dimensions. We only experience the trickle that remains. The graviton isn't weak, it's just diluted. We have struggled to detect it for the same reason it's hard to feel the warmth of a bonfire from miles away. Its energy is radiating out into a much larger space than we can perceive, leaving our universe gravitationally anemic. The silence in our detectors, then, is not the sound of absence. It is the sound of escape, the sound of gravitons slipping through the cracks of our reality, journeying into a hidden cosmos, just a quantum leap away from our own. It is a vision of staggering beauty and scope, a universe of unimaginable complexity, a cosmic membrane floating in a higher dimensional hyperspace, with gravity acting as the sole messenger between our world and the vast hidden reality beyond. But this is not the only path through the wilderness. Opposing this grand orchestral vision is another equally compelling and profoundly different idea. It does not seek to add new dimensions to our universe. Instead, it seeks to shatter the very dimensions we thought we knew. This is loop quantum gravity. Where string theory is expansive and additive loop, quantum gravity is minimalist and revolutionary. It begins not with the ambition to unite all forces, but with a far more focused and arguably more humble goal: to take Einstein's general relativity, our reigning theory of gravity and space-time, and subject it to the brutal, unforgiving laws of quantum mechanics. It performs this forced marriage without inventing new particles or extra dimensions. It uses only what is already there. And in doing so, it arrives at a conclusion that is, if anything, even more shocking than that of string theory. It concludes that space-time itself is not fundamental. The smooth, continuous geometric backdrop of our existence, the very stage on which the cosmic drama unfolds, is an illusion, an approximation that only appears smooth from a distance. If you could zoom in far beyond the scale of atoms, beyond quarks, down to the impossibly small Planck length of distance, 100 billion times smaller than a proton, you would find that space is not empty and continuous. You would see that it is granular. You would discover that reality is in a very literal sense pixelated. Loop quantum gravity proposes that the fabric of the universe is not a seamless sheet of silk, but an intricate, indivisible weave. Space-time at this fundamental level is a network, a seething dynamic web of interconnected nodes and links. These connections are not objects times in time-space. They times a time-space. Each link in this network, each loop, represents a fundamental, indivisible quantum of area. Each node where these loops intersect represents a fundamental quantum of volume. You cannot have a smaller area or a smaller volume, just as you cannot have half a photon or half an electron. These are the atoms of space itself. Geometry in this picture is not a given, it is emergent. The very concepts of distance, area, and volume are built up from the collective relationships of these countless quantum loops, like a digital image emerging from a vast grid of discrete pixels. This is a universe where there is no stage. There are only the actors, the fields and particles, and the relationships between them. The network of relationships times the geometry of the universe. This quantum tapestry is constantly reconfiguring itself, its threads snapping and reforming in a dizzying quantum dance. This dynamic evolution, this constant rewriting of the connections in the network, is what we perceive on a macroscopic scale as the flow of time and the curvature of space-time. Gravity is not a force transmitted times across time-space. Gravity is the very structure of the quantum weave itself. It is the collective behavior of the atoms of space. So where is the graviton in this pixelated reality? The answer is as profound as it is disruptive to our quest. In loop quantum gravity, the graviton is not a fundamental particle, that you can isolate and detect in a lab. It is not a messenger traveling through space-time. Instead, a graviton is a collective excitation times of time's space-time. It is a ripple, a propagating vibration, a specific organized tremor passing through the quantum network itself. Think of the surface of a pond. A water molecule is a discrete thing, but a wave is not. A wave is a pattern of collective motion among countless water molecules. You cannot capture a wave in a bucket. You can only observe its effect as it passes. Loop quantum gravity suggests the graviton is like that wave. It is a quantized pattern of disturbance in the underlying quantum geometry. It is less a thing and more of a behavior, a coordinated shiver running through the atoms of space. This completely reframes our hunt. It suggests that our quest to build a detector to catch a single graviton might be as misguided as trying to build a net to catch a single musical note. The failure of our detectors might not be due to gravity's weakness, but due to a fundamental misunderstanding of its nature. We have been searching for a bullet when we should have been listening for a drumbeat. We have been hunting for a particle when gravity may not be a particle at all, but a pattern woven into the very fabric of existence. Here, then, is the great chasm that defines the frontier of modern physics. On one side, the sweeping unified vision of string theory with its symphony of vibrating strings and its universe of hidden dimensions. It gives us a beautiful, necessary graviton, but at the cost of a reality far more complex than we can see, operating according to rules we can only infer. It is a top-down approach, a grand attempt at a final theory of everything that frustratingly seems to describe an infinite number of possible universes, with no clear reason why we should find ourselves in this particular one. On the other side stands the stark, focused revolution of loop quantum gravity, a bottom-up approach that rebuilds reality from its most basic geometric components, giving us a granular, pixelated spacetime. It explains gravity as an intrinsic property of this quantum network, but it struggles to incorporate the other forces of nature and the particles of the standard model. It offers a radical new view of our universe, but has yet to prove it can describe the whole of it. These two pictures of reality are utterly irreconcilable. One requires a smooth, continuous, multidimensional background for its strings to vibrate within. The other insists that no such smooth background exists. There is only the quantized granular network itself. One sees the graviton as a fundamental free-roaming particle. The other sees it as an emergent collective ripple in the fabric of space. They cannot both be right. This is the great intellectual crisis of our time. We have arrived at the edge of the map and found two completely different continents, both drawn with the impeccable logic of mathematics, yet mutually exclusive. And the dilemma that haunts every physicist working on these theories is the profound, terrifying question of how we could ever possibly choose between them. Both theories make their most dramatic predictions at the Planck scale, an energy regime so extreme, so far beyond our technological reach, that building a machine to probe it directly would require a particle accelerator the size of our galaxy. The vibrating strings and quantum loops are for now confined to the realm of pure mathematics. They inhabit a world of thought seemingly sealed off from any possible experiment. The silence from our detectors has forced us into this abstract domain, and this domain in turn has presented us with a choice we seem incapable of making. We are adrift in a sea of breathtaking ideas, with no empirical compass to guide us to shore. The hunt for the graviton has led us to the deepest questions humanity can ask. What is the ultimate nature of space and time? Is our universe unique or one of many? Is reality continuous, or is it built from discrete, indivisible blocks? These questions, born from a search for a single particle now, hang in a theoretical void, mocking us with their grandeur and their apparent untestability. The path forward has vanished. If we cannot build a machine powerful enough to see these hidden worlds directly, if we cannot journey to the quantum realm to witness its structure for ourselves, how can we ever hope to know the truth? We must find another way, a cleverer way. We must learn to search not for the things themselves, but for their shadows, their faint echoes left behind on the cosmos from a time when the universe was hot enough and dense enough to put these very theories to the ultimate test. Here, at the very edge of our perception, the trail seems to go cold. The hunt for the Graviton, this grand quest for the final missing piece of the puzzle, appears to end not with a triumphant discovery, but with an unnerving cosmological silence. We have built our theoretical traps, laid our observational snares across the fabric of space-time, and listened with unparalleled patience. For decades, we have strained to hear the whisper of a single quantum of gravity, the fundamental note in the universal symphony. Yet the universe has offered only the echoes of its larger movements, the classical sweeping chords of Einstein's relativity. The particle, the tangible messenger of the gravitational force, remains a ghost, a phantom haunting the pristine equations of our most successful theories. This silence could feel like a failure, a grand anticlimax. You might be forgiven for thinking that our journey, which has taken us from the mind of Einstein to the heart of colliding black holes, has led us to an impassable wall, an ultimate cosmic dead end. But in science, and especially in the search for fundamental truth, an answer of no is never just an ending. Often, it is the most profound kind of beginning. The empty trap tells you something vital about the nature of the creature you are hunting. Sometimes the most important discoveries are not the things we find, but the radical new questions we are forced to ask when we find nothing at all. The very absence of the Graviton, its stubborn refusal to appear in our models and our detectors, has become the catalyst for the greatest paradigm shift in a century. It has ignited a revolution not of discovery but of perspective. The conflict between the smooth geometric universe of general relativity and the frenetic quantized world of quantum mechanics, a conflict crystallized in this single missing particle, has pushed humanity to the brink of imagination. We arrived at this point seeking a messenger particle, a simple cog in the cosmic machine. We now find ourselves questioning the nature of the machine itself. We are being forced to consider possibilities so profound, so utterly counterintuitive, that they challenge our deepest assumptions about what reality even is. The silence of the Graviton is not the sound of failure. It is the sound of a door creaking open, revealing a landscape of ideas more bizarre and more beautiful than we could have ever conceived. In this new unsettling light, we are beginning to see that perhaps we were never just hunting for a particle. Perhaps unknowingly we were searching for the soul of the universe itself, and the price of admission was letting go of everything we thought we knew. The chasm that opened between our two great pillars of physics had become an intractable abyss. On one side stood the majestic, deterministic world of Einstein, a universe of curved space-time, where gravity is the elegant geometry of planets waltzing through cosmic valleys. On the other side stood the chaotic, probabilistic world of quantum field theory, a realm of ephemeral particles popping in and out of existence, where all other forces are conveyed by discrete packets of energy. For years, physicists tried to bridge this gap, to pave a road across the divide with the Graviton as its keystone. Every attempt crumbled. The mathematics broke down into nonsensical infinities. The theories predicted absurdities. The missing Graviton was no longer just a missing particle. It became the ultimate symbol of our broken understanding, the embodiment of a fundamental incompatibility at the heart of creation. This crisis, born from decades of frustration, became the fertile ground for a new generation of thought. Instead of asking, how do we force these two theories together, a radical new question began to be whispered in the halls of theoretical physics. What if one of them is not as fundamental as we believe? What if gravity isn't a force to be, quantized in the first place? What if it's something else? Entirely. This single, audacious thought experiment gave birth to one of the most compelling and strangest ideas in modern science, the theory of emergent gravity. It proposes that gravity is not a fundamental interaction woven into the basic source code of the universe. Instead, it might be an emergent phenomenon, a secondary effect, something that arises from the collective behavior of more fundamental hidden components of reality. Much like temperature or pressure arise from the chaotic dance of countless individual atoms, a single water molecule has no temperature. It has kinetic energy, yes, but the concept we call temperature is a statistical illusion, a meaningful average that only emerges when you have trillions of molecules interacting together. A single molecule isn't wet. Wetness is a property born from the collective, from the relationship between a vast number of molecules. What if gravity is like that? What if it's the temperature of the cosmos? What if the smooth, continuous fabric of space-time that we perceive is like the surface of a seemingly placid lake, actually composed of a staggering number of discrete, microscopic constituents we have yet to even imagine is this radical retelling of our universe? There are no gravitons, no force-carrying particles for gravity for the same reason. There is no fundamental particle of wetness or pressure. Gravity in this view is an epiphenomenon. It is the universe's way of handling information. Some theories of emergent gravity link it directly to the laws of thermodynamics, suggesting that gravity is not the cause of cosmic order, but a consequence of the universe's relentless tendency towards disorder, towards maximum entropy. It's a concept that demotes gravity from its regal status as a primary force of nature. It recasts it as a kind of cosmic accounting principle, a thermodynamic pressure exerted by the universe's own information content. If this is true, our long and difficult hunt for the graviton was always destined to fail. We were chasing a ghost. We were searching for a single raindrop in a cloud, without realizing that the very phenomenon of weather is what we should have been studying all along. This idea is profoundly unsettling because it suggests that the stage upon which the cosmic drama unfolds, space-time itself, may not be a fundamental stage at all, but a construct, a collective illusion conjured by the interplay of deeper, unknown elements. This notion that information might be more fundamental than space and time led to an even more breathtaking possibility, an idea that leapt from the esoteric study of black holes to encompass the whole of reality. It is known as the holographic principle, and it might be the single most mind-altering concept in all of science. It too grew from the profound conflict between general relativity and quantum mechanics. When a star collapses into a black hole, all the complex information that made up that star, every particle, every atom, every quantum state, seems to vanish behind the event horizon, lost forever. This posed a terrifying problem for quantum theory, which has, as its most sacred tenet, the rule that information can never be truly destroyed. The universe, according to quantum mechanics, must keep a perfect record. For decades, this information paradox raged. Then a crucial breakthrough was made. Physicists like Jacob Bekenstein and Stephen Hawking discovered a stunning connection. The maximum amount of information you could possibly cram into a region of space is not proportional to its volume, as you would intuitively expect. It is proportional to the area of its surface, the boundary that encloses it. It was as if you tried to store books in a warehouse only to find that the building's storage capacity was determined not by the size of the room inside, but by the square footage of its walls. This was the seed of the holographic principle. It suggests that the information content of our three-dimensional universe might be entirely encoded on a two-dimensional surface at its farthest boundary. Think of a security hologram on a credit card. It's a flat two-dimensional surface, but when light reflects off it, it produces a fully realized three-dimensional image. The holographic principle proposes that our universe works in a similar way, that we and everything we perceive, every galaxy, every star, every atom, the very sensation of depth and volume could be a complex projection, a grand illusion generated from a thin layer of information located on some distant cosmological horizon. This isn't just a philosophical fancy. It is a mathematically rigorous idea that has become a cornerstone of modern theoretical physics, particularly in the context of string theory, and its implications for gravity are staggering. In this holographic model, the universe in which the information is encoded, that distant 2D surface, is a world without gravity. It's a purely quantum world governed by the familiar rules of particle physics. But the mathematics shows that when you project this information into one higher dimension, creating the 3D hologram we perceive as our reality, a new force magically appears in the equations. That force is gravity. Gravity in the holographic universe is the thermodynamic ghost of a non-gravitational system in a lower dimension. It is the geometric manifestation of quantum entanglement on the boundary. This would elegantly explain why gravity seems so different from the other forces, why it's so extraordinarily weak. It's because it's not playing on the same field. It's a diluted force, a shadow of more fundamental interactions happening elsewhere on the true stage of reality. The graviton in this picture becomes a complex composite, not a fundamental entity. Trying to find it would be like examining the 3D image of a person from a hologram and trying to find the single pixel of their existence on the 2D film. The very concept is flawed. The entire image emerges as a whole from the underlying code. So too, perhaps, does our universe. It challenges our sense of self, our place in the cosmos. Are we the actors in the play, or are we merely the flickering images projected onto the stage? The holographic principle suggests that the fundamental reality may lie not here in the space we inhabit, but on the edge of everything, in a blueprint of pure information from which our world is born. Whether gravity is emergent or holographic, both ideas point towards a shared revolutionary conclusion. The smooth, continuous canvas of space-time, described by Einstein, must break down at some ultimate infinitesimal scale. If we could zoom in far beyond the scale of atoms, beyond even protons and neutrons past the quarks, down to the theoretical limit of distance itself, the Planck length, a billionth of a trillionth of a trillionth of a centimetre, the universe would look nothing like we know. Down there in that unimaginable realm, the conflict between general relativity and quantum mechanics is no longer a polite disagreement. It is a violent, raging war. Quantum theory insists that this tiny patch of reality must be a bubbling cauldron of uncertainty. The Heisenberg uncertainty principle, when applied to space-time itself, implies that space and time cannot be perfectly still or perfectly flat. They must fluctuate. They must boil. This theoretical texture of reality, at its most fundamental level, is what physicists call space-time foam. Imagine a sea of pure energy where tiny virtual black holes and wormholes can wink into existence for a fleeting instant before annihilating one another. A chaotic, unpredictable storm where the very concepts of here and there, of before and after, lose their meaning. This is the domain where gravity must become a quantum phenomenon. The elegant curvature of space-time must dissolve into a probabilistic froth, and for our journey this concept is crucial. Because if space-time is a foam, then it is not a perfect medium for travel. Anything moving through it, even light and especially a gravitational wave, would be subtly affected by this quantum texture. It would be like trying to navigate a perfectly straight line across a churning ocean. From a great distance, the path may look smooth, but up close the ship is constantly being nudged and jostled by the microscopic chaos of the waves. For the first time, this gave us something tangible. It gave us a potential signature, a clue that we could perhaps one day observe. The theories of emergent gravity and the holographic principle are beautiful, but they exist primarily on blackboards and in the minds of theorists. Space-time foam, however, might just leave fingerprints on the cosmos. It suggests that the grand sweeping gravitational waves from colliding black holes, the very phenomena Einstein predicted, might carry a secret message hidden within their ripples. A message from the quantum world. As these waves travel for millions or billions of years across the universe, they are passing through an unfathomable amount of this potential foam. Each microscopic fluctuation could impart an infinitesimal distortion, a tiny amount of scattering or dispersion. The wave that arrives at Earth would not be the pristine, perfect wave that left its source. It would be subtly blurred, slightly fuzzed, carrying the faint, cumulative scars of its journey through the quantum realm. The hunt for the graviton particle may have stalled, but a new hunt had just begun. A hunt for the texture of space-time itself. And for this new hunt, we have built the most sensitive listening devices in the history of humankind. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its partners Virgo in Europe and Kagra in Japan, were conceived to do one thing: to detect the macroscopic ripples in space-time predicted by general relativity. They are celestial seismographs of staggering precision, capable of measuring a distortion in space smaller than 1/10,000th the width of a single proton. Their initial triumphant discovery of colliding black holes in 2015 was a confirmation of Einstein's genius, a masterpiece of classical physics. But their true long-term mission may be far more revolutionary. These incredible instruments are our first and only probes with the potential to touch the world of quantum gravity. They are not detectors in the traditional sense, searching for a particle that goes times ping asterisk. Instead, they are looking for something far more subtle. They are listening for the telltale signs of imperfection in the drumbeat of space-time. As hundreds of gravitational wave events are catalogued and analysed with increasing precision, we are no longer just confirming that Einstein was right. We are now searching for the tiny, almost imperceptible ways in which he might have been incomplete. We are looking for anomalies. Does the wave's shape deviate even slightly from the perfect form predicted by the classical equations? Does its polarization twist in an unexpected way as it travels? Do high-frequency waves travel at a vanishingly different speed than low-frequency waves, a phenomenon forbidden in classical relativity, but predicted by some theories of space-time foam? This would be a signature known as cosmic birefringence, a faint echo of the universe's quantum graininess. The noise itself within the detectors is another frontier. Buried within the constant hum of terrestrial vibrations and thermal fluctuations could be a more fundamental noise, the ceaseless crackle of space-time foam itself. Some theories predict a background of high-frequency gravitational waves generated by this quantum chaos, a universal, ever-present hiss that could, in principle, be detected by future, even more sensitive observatories like the laser, interferometer, space antenna, or LISA. LISA will be a constellation of 3 spacecraft, forming a giant triangular detector in space, with arms millions of kilometers long, far from the noisy seismic interference of Earth. It will be an observatory so sensitive that it might hear the quantum jitters of reality. We are in a very real sense learning to listen to the silence. The same silence that met our search for the Graviton particle is now the canvas upon which we hope to find the signature of its underlying reality. We are sifting through the data from these cosmic cataclysms, looking for the faintest of whispers, the most tenuous of clues that the universe at its heart is not smooth but pixelated, that space-time is not a stage but an actor. Each new gravitational wave that washes over the Earth is another data point, another chance to glimpse beyond the classical veil. The pursuit has transformed. It has matured from the brute force search for a single target to a sophisticated interrogation of the very nature of space and time. So the climax of our story is not the capture of a fugitive particle. It is a profound and humbling revelation about the nature of our quest. The relentless pursuit of the Graviton, in its spectacular lack of success, has done something far more important than its discovery ever could have. It has shattered our old certainties and forced us to confront a universe far stranger and more deeply interconnected than we had ever dared to imagine. We embarked on a journey to find the final piece of a familiar puzzle, only to find that the puzzle itself was an illusion, and that beneath it lies a new mosaic of reality, whose full pattern we are only just beginning to trace. We haven't found the Graviton, and we may never find it in the way we originally expected. But in looking for it, we have found a new cosmos. We have discovered that gravity might not be a force at all, but a collective whisper from a hidden dimension, a thermodynamic consequence of information. We have learned to see the universe as a potential hologram, a projection of a deeper truth, and we have built machines that can hear the shuddering of space-time, turning them into our first tentative microscopes for exploring the quantum structure of reality. The conflict between the world of the very large and the world of the very small has not been resolved. But it has given birth to a new era of physics, an era of breathtaking ideas that stand as testament to the power of the human imagination when confronted with the vast, silent mystery of the unknown. We are no longer just physicists. We are cartographers of reality itself, and the maps we are drawing are leading us to the very edge of existence. And so our journey, which began with the simple terrestrial fall of an apple, now finds us adrift in the boundless conceptual ocean of quantum reality. We have walked the hallowed halls of history, standing shoulder to shoulder with Newton as he first penned the universal law that binds the heavens to the earth. We have travelled on a beam of light with a young Einstein, witnessing the very fabric of space-time bend and warp, reimagining gravity not as a force, but as the intimate curvature of existence itself. We then plunged headlong into the bewildering, paradoxical world of the quantum, a realm where particles are waves, where certainty dissolves into probability, and where the other three forces of nature dance to a strange and unified rhythm. Through it all, our compass has been the hunt for a single ghost-like particle, the graviton. This phantom messenger, this theoretical quantum of gravity, has been our North Star, guiding us through the most profound intellectual revolution in human history. We sought a simple, elegant confirmation, a final puzzle piece that would snap the two great pillars of modern physics, general relativity and the Standard Model, into a single, magnificent edifice. What we found instead was a chasm, an abyss separating the world of the very large from the world of the very small, a conceptual divide so deep and so violent that it has shaken the very foundations of our understanding. Our quarry, the graviton, has remained elusive, a whisper in the equations, a ghost in the machine. Yet this is not a story of failure. It is perhaps the most important story of scientific success ever told, for the true value of a great quest lies not in the prize you capture, but in the map you are forced to draw along the way. The absence of the graviton, the deafening silence from the quantum depths of gravity, has been its most eloquent and transformative message. It has told us in no uncertain terms that our map is incomplete, that the universe is infinitely more subtle, more interconnected, and more magnificent than we had dared to conceive. This supposed failure has been the ultimate catalyst, the intellectual irritant that has provoked the birth of new, beautiful, and radical pearls of thought. It has forced us to ask questions that would have sounded like madness a century ago. Is space itself not fundamental but an emergent property, a shimmering hologram projected from a lower dimensional boundary? Are the particles we see not tiny points at all, but the resonant vibrations of unimaginably small, open, and closed loops of energy? Is the universe just one of a vast, infinite collection of other universes, a single bubble in a churning cosmic foam? These questions, born from the frustration of our hunt, have become the foundational inquiries of 21st century physics. They have fractured the singular path forward into a breathtaking delta of possibilities, a vibrant landscape of competing ideas, each one a potential Rosetta Stone for decoding the ultimate language of the cosmos. On one continent of this new world, you find the elegant architecture of string theory. Here, the frustrating infinities that arise when you try to quantize gravity are miraculously tamed. The graviton is no longer a problematic point particle, but a specific, graceful vibration of a closed string, a tiny loop of pure energy singing the song of space-time. To its adherents, string theory is not merely a solution, it is an inevitability, a framework of such profound mathematical consistency that it seems at times must times be true. It gives us not just the graviton, but a veritable symphony of particles unifying all of creation into a single harmonious score. But this harmony comes at a cost, demanding the existence of extra hidden dimensions of space curled up so tightly that we have never perceived them. It presents us with a landscape of possible universes so vast that finding our own within it feels like an almost impossible task. It is a theory of staggering beauty and tantalizing promise, yet one that has so far struggled to make concrete predictions we can test with our current technology. It remains a grand cathedral of the mind, its spires reaching for a heaven we cannot yet see. Journey to another continent on this intellectual map and you will find the rugged, granular terrain of loop quantum gravity. This approach is more conservative, more grounded in the lessons of Einstein himself. It does not demand extra dimensions or a symphony of new particles. Instead, it takes Einstein's greatest insight, that gravity times is time's geometry, and pushes it to its absolute quantum conclusion. In this view, space-time itself is not a smooth, continuous fabric. If you could zoom in to the smallest possible scale, the Planck scale, you would find that space is built from discrete, indivisible chunks, tiny atoms of geometry. These are the loops, intricate networks of interconnected nodes that literally weave the fabric of reality. Space-time and geometry are in this vision quantized. The universe at its most fundamental level is not a stage, but a dynamic, evolving network of relationships. There is no background. There is only the ceaseless, intricate dance of these quantum loops. The graviton in this picture is not a fundamental particle traveling through space, but rather a collective excitation, a ripple propagating through the quantum geometric network itself, much like a sound wave is a ripple traveling through the air. It is a profoundly different vision of reality, one that sees the cosmos not as a painting on a canvas, but as the canvas itself constantly reweaving its own existence. It offers a stunning resolution to the problem of singularities within black holes, and at the Big Bang, suggesting that the universe did not begin from an infinitely dense point, but perhaps bounced from a previous cosmic era. And beyond these two great continents lie other stranger islands of thought, archipelagos of radical ideas that challenge our most deeply held assumptions. Some physicists wonder if gravity is fundamentally different from the other forces, an entropic phenomenon that emerges from the laws of thermodynamics, much like temperature emerges from the motion of atoms. In this view, gravity is not a fundamental interaction at all, but a statistical inevitability, the universe's tendency toward disorder made manifest as the curvature of spacetime. Others pursue the idea of asymptotic safety, suggesting that the unruly behavior of gravity at high energies might be tamed by a hidden fixed point in the equations, a cosmic thermostat that prevents the infinities from running wild. Still others explore causal set theory, which proposes that the fundamental reality is a discrete collection of spacetime events linked by a web of cause and effect with the geometry of our universe emerging from the structure of this cosmic network. Each of these theories is a testament to the raw power of human imagination, a direct consequence of the graviton's refusal to be easily found. The hunt has not led us to a dead end. It has blasted open the entire landscape, revealing a universe of possibilities far richer and more varied than the simple mechanistic cosmos of a bygone era. We are living in a heroic age of physics, an era of exploration not of new lands but of new realities. This journey of the mind is now being matched by a new generation of explorers, building monumental machines, colossal instruments designed to listen for the universe's most subtle secrets. For most of scientific history, our view of the cosmos has been almost entirely reliant on light on the electromagnetic spectrum, but we have recently opened a new window, a completely new sense with which to perceive reality: gravitational waves. The Laser Interferometer Gravitational Wave Observatory, or LIGO, and its partners have already allowed us to hear the violent collisions of black holes and neutron stars, events that are completely dark to our conventional telescopes. These first whispers from the gravitational universe have confirmed Einstein's predictions with breathtaking accuracy, but this is only the beginning. Soon we will take this new sense into space itself. The Laser Interferometer Space Antenna, or LISA, will be an observatory of truly cosmic proportions. 3 spacecraft flying in a perfect triangular formation millions of kilometers apart will be linked by laser beams. This immense celestial instrument will be sensitive to the slow, gentle swells of the gravitational ocean, the low-frequency waves produced by the mergers of supermassive black holes, the cosmic titans that lurk in the hearts of galaxies. LISA will be able to detect the gravitational ripples from the universe's infancy, potentially hearing the echoes of the Big Bang itself. If inflation, the theory of the universe's explosive first moments, is correct, it should have flooded the cosmos with a primordial background of gravitational waves. Seeing this background would be like seeing the flash of creation, and studying its properties, its quantum fluctuations, could provide the first tantalizing indirect evidence of the graviton. At the same time, we continue to push the frontiers of energy. The Large Hadron Collider and its potential successors are designed to smash particles together with such violence that they recreate the conditions of the early universe. While we are unlikely to produce a graviton directly, its interaction is so weak it would almost certainly fly through our detectors unnoticed. These experiments could reveal evidence of the strange new physics predicted by theories like string theory. The discovery of supersymmetric particles, or evidence of those elusive extra dimensions, would be a seismic shock, a signpost pointing us firmly in one direction on that vast map of possibilities. And we continue to look outward, not just with gravitational waves, but with ever more powerful telescopes. By precisely mapping the distribution of galaxies and the faint afterglow of the Big Bang, the cosmic microwave background, we can test our theories of gravity on the largest possible scales. Any deviation from the predictions of general relativity in the cosmic structure could be a clue, a faint crack in Einstein's magnificent edifice that hints at the deeper quantum structure beneath. We are attacking this problem from every conceivable angle, from the highest energies in our colliders to the lowest frequencies in the gravitational wave spectrum, from the smallest theoretical scales to the largest observable structures in the cosmos. We are, in effect, building a web, a net of unprecedented size and sensitivity, hoping that somewhere within its threads we will finally catch our ghost. So, what is the ultimate prize? What lies at the end of this extraordinary intellectual journey? Finding the graviton, or understanding why it cannot be found in the way we expect, is about so much more than completing a set of particles in a textbook. It is about reaching the very bedrock of reality. It is about understanding how the universe is built. A theory of quantum gravity, the holy grail of modern physics, would be our final answer to the oldest questions our species has ever asked. What is space? What is time? Where did it all come from? A true theory of everything would not just unite the forces of nature. It would unite the microscopic world of quantum mechanics with the macroscopic cosmos of general relativity. It would describe the birth of the universe from the quantum foam and the fate of matter falling into the quantum heart of a black hole. It would provide us with the ultimate set of rules, the source code of creation. It would be, in a very real sense, the final chapter in a story that began when the first human looked up at the night sky in wonder. To possess such a theory would be to see the universe with new eyes, to understand the deep and unbreakable unity that underlies all of existence. The atoms in your body, the light reaching you from a distant star, the chair you are sitting on, and the inexorable pull of the earth beneath you would all be revealed as different expressions of the same fundamental reality. The elegant mathematics of such a theory would be the ultimate poem, a description of the cosmos of such power and beauty that it would represent the pinnacle of human intellectual achievement. It would be a testament to that most unique and precious quality of our species, our insatiable, unyielding curiosity. The drive to know, to understand, to look past the horizon is what took us out of the caves and onto the moon. It is what fuels every scientist, every philosopher, every artist. It is the engine of our civilization. The hunt for the graviton is the modern-day embodiment of that ancient quest. It is our generation's cathedral to build our voyage into the unknown. We do not know when or even if this search will reach its conclusion. We may find the graviton tomorrow. We may find evidence for strings or loops, or something far stranger than we can currently comprehend. Or the mystery may deepen, leading us down paths we cannot yet even imagine. But this much is certain: the journey itself has already transformed us. In searching for the smallest, weakest, and most elusive piece of the puzzle, we have been forced to grapple with the biggest and most profound ideas. We have had to confront the limits of our intuition and embrace a cosmos that is fundamentally weird, wonderfully non-intuitive, and breathtakingly beautiful. The legacy of the graviton hunt is the realization that reality is not a fixed stage on which events unfold, but a dynamic, interconnected, and evolving process. We are not merely observers of this universe. We are a part of it, forged from the same quantum essence that we so desperately seek to understand. Our quest is not an external one. It is the universe through us, attempting to comprehend itself. The path ahead is long and the challenges are immense, but for a species defined by its desire to reach for the stars, there can be no more noble, no more vital, and no more human endeavor than this. The hunt continues.